So in the previous example, we found the normal and tangential component of the acceleration for an easy to visualize, so to speak, a vector valued function, which is the parametric form of a circle. That way, so we can easily make sense about what we're doing. Now, let's have a look at a more elaborate case. Well, for this vector valued function number one in space, that is t squared, 2t squared, and t cubed. So, and again, in this case, I'm going to use the second alternative formula for the for the acceleration, for the normal component of the acceleration. Well, first of all, let's find the derivative, that is the velocity. That is 2t, 6t, 3t squared. And acceleration, that is 2, 6, 6t. Okay? Alright, well, for the tangential, we need the velocity function and its magnitude. So let's get the magnitude of v. That is the square root of 2t squared plus 6t squared plus 3t squared squared. So that is going to give us, well, the square root of 4t squared plus 36t squared plus 9t squared squared. That's t to the fourth. Okay, let's simplify this as much as we can. So, are we? Yes, okay, let's do that in a second. Okay, so that's going to be the square root of, simplify 36 plus 4, that's 40, t squared plus 9 t to the fourth. Notice how we could factor out a t squared. That's 40 plus 9 t squared. Alright, and the square root of t squared, well, I know technically it should be the absolute value of t because we have no idea about what's the value of t, but in this case, let's just assume that we're looking only at positive values of t, like, well, I mean, we're going forwards in time, not back in time, right? I mean, even though, I mean, depending on how we set this parameterization, it's possible to look at negative values of time. So, but let me just take the positive case. That is the square root, t square root of 40 plus 9t squared. Okay. So let's get the tangential, the unit tangent vector. That is big T of t equal to the magnitude, or rather the velocity, divided by its magnitude. Or using the other notation, recall that v is r prime over the magnitude of r prime, either way. Alright? So that is v, the velocity, which is 2t, 6t, 3t squared over t times the square root of 40 plus 9t squared. And we'll notice how in this case we can reduce factors of t, so that's why it was a great idea to factor out this t outside of the radical. Otherwise, it would have been a mess to get all these radicals with fourth powers inside and the like. So let me reduce this to lowest terms. So this will be 2, 6, 3t, everything divided by the square root of 40 plus 9t squared. Alright? I know, you might be thinking, you might want to think of distributing the square root over the 3 terms. Well, actually we're going to perform a dot product in a second, and well, you don't want to write this many terms. So that's actually, by the way, then what's next. So a sub t, that is the tangential component of the acceleration, that is the acceleration vector, which we got over there, dotted with what we just found, that is, oh, this is not big T prime, this is just big T, by the way. Big T of T, that is the acceleration 2, 6, 6t dotted with 2, 6, 3t divided by this humongous radical there. That is 40 plus 9 t squared. Well, let's do the dot product here in the numerator. That's going to give us, well, 2 times 2, that equals to 4. 6 times 6 equals 36. And 6t times 3t, that's 18t squared. Divided by the square root of 40 plus 9t squared. Combining like terms, that's 4 plus 36, that equals to 40 plus 18t squared over the square root of 40 plus 9t squared. So in this case, it's not 0 like in the previous case. Actually, we're getting, and not even a constant value. It's a variable value because it's not a perfectly circular trajectory this time. So we're going to have a very irregular curve for which the curvature is going to be different at every single point. The unit tangent vectors are going to point in different directions, as well as the unit normal vector. The acceleration as well is going to change depending on the point. So that's explained by these different values of t. All right. Okay, let's go ahead and do number 2. For number 2, a sub n, the acceleration times the unit normal vector. All right. But hold on, again, you don't want to do big N the long way we did it before, right? We would have to find the second derivative, actually two chain rules and one quotient rule, and you don't want to do that. It's going to be overwhelming. So, okay, so instead, again, let me cross this out, and I'm going to use the alternative. So the alternative will be the magnitude of the cross product between the velocity and the acceleration divided by the magnitude of the velocity. And again, it's not the velocity cube. The velocity cube is to calculate the curvature. All right. So what do we need? Oh, we need the cross product between acceleration and velocity. Okay. Acceleration cross velocity. That's gonna be okay. The velocity. Oh wait. Well, actually, I did this the reverse way for this exercise. So let me just go with what I have on my notes. I don't want to improvise. 2, 6, 6t, and 2t, 6t, and 3t squared. Anyway, we will still find the magnitude of this vector, and well, that's just going to be a positive result. All right, so let's repeat the first two columns. Or again, if you want to use the definition, which is by expanding by cofactors and minors, well, that's up to you. But again, I prefer to use Sarus's rule, which is a lot quicker, I think. Okay. Multiplications of elements along the main diagonals, that is 6 times 3, that's 18, t squared I, j times 6t times 2t, so that is 12t squared, j, and 6t times 2 times k, that is 12tk. So that is the result of the multiplications of the elements of the three main diagonals. Now let's do the reverse. Okay, that is j times 2 times 6t squared. That is a minus. That is 6t squared j. I times 6 times 6, that's 36t squared I. And last but not least, 6 times 2, which is 12 times t times k, that is 2tk. Or, yeah, 12tk. Alright? Alright. So combining like terms right here, that should give us the following. I'm going to go component form. So the i's with the i's, that is 18 minus 36. That's going to give us negative 18. T squared, comma. J's with j's, that is 12 minus 6. T squared for both. That's a 6t squared. And lastly for the k's, 12tk minus 12tk, actually 0. Alright, so that's just the cross product between the acceleration and the velocity, or velocity and acceleration. Either way, if you did it the other way, velocity times acceleration, you would have gotten plus, minus, and well, 0, it's still 0. Right, you just get the components with the opposite sign. However, we're going to find its magnitude, so let me add another page. So you might want to use the back side of the page for this, because it's still going to take another good minute to go. Alright, so what's that? What else do we need? We need the magnitude of A cross V. That is the square root of negative 18 t squared plus 6 t squared plus 0 squared. Alright, so that is the square root. Okay, 18 squared, big number, that is 324 t to the fourth plus 6 squared, which is 36, t to the fourth also. 0 squared, it's still just 0. So let's just combine terms. 324 plus 36, that equals 360 t to the fourth. And we may simplify this expression a bit further, because number one, the square root of t to the fourth, that's t squared. And here, 360 is the same as 36 times 10, where 36 is a nice perfect square. The square root of 36, that's going to be 6. And I'm going to write the square root of 10 multiplying at the very end. All right? So that's as far as we can simplify this. And we're ready to find the normal component. That is a sub n, that is magnitude of the acceleration cross the velocity, or vice versa, divided by the magnitude of the velocity. That is negative 6t squared root of 10 divided by the magnitude of the velocity. But didn't we get that in the previous part? Let me go back. That was this quantity, t root of 40 plus 9t squared. Okay, so t root of 40 plus 9t squared. Okay, t squared over t in the numerator, that equals to 6t root of 10 divided by the square root of 40 plus 9t squared. Okay? And that's the normal component of the acceleration. So now what does that mean? So this means that the acceleration, the acceleration vector, which is a sub t plus a sub n, big N, that equals a sub t, which is 40 plus 18 t squared over the square root of 40 plus 9t squared times the tangential plus a sub n, which is the quantity we just found, that's 6t root of 10 over the square root of 40 plus 9t squared. That times big N. So again, this quantity right here, this variable expression, is going to tell us the scalar projection of the acceleration onto the tangential, and this expression, this variable expression, is going to give us the scalar projection of the acceleration onto the normal vector. In other words, this is the magnitude of the shadow, the acceleration in the direction of the tangential, and this is the magnitude or the length of the shadow of the acceleration onto the normal vector, on towards the concave side. All right, and I believe this finishes the section. And